So here we have a function in two variables, and we're going to try to find the critical points. Remember, these are where the derivative with respect to x and the derivative with respect to y are equal to 0 at the same time. Okay, so we're going to take our partial with respect to x and our partial with respect to y and set them both equal to 0 and see what happens. All right, so let's take our partials of this function. We're going to find the partial with respect to x. All right, and let's see, I got 1/3 times the derivative of x cubed, 3x squared, and minus x, I just get -1. And then the rest of the function is just made up of a bunch of y's, so the derivative with respect to x is 0. So I could simplify my derivative with respect to x, cancel out the 3 and the 1/3, and I just get x squared minus 1. All right, so we're going to set that equal to 0 in a second. Let's come find our partial with respect to y. So again, anything that's just x's is getting wiped out by this derivative, so I'm just left with the y stuff on the right. 1/3, 3y squared, and then minus 4. And again, these lovely pre-rigged coefficients cancel out, and I get y squared minus 4. All right, so we're going to set both of those equations equal to 0. And this one is kind of an oversimplified function because both partials end up just having one variable in each equation. We'll do another one that's a little bit more complicated in a bit. So I'm going to set both partials equal to 0 and just solve and see what I get. All right, so I've got x squared. I can add 1 to both sides. I'm going to take a square root of both sides. Anytime the square root is my idea, I need a plus or minus, so I get x plus or minus 1. And then over here for partial with respect to y, same thing. I'm going to add 4 to both sides and apply my square root. And I get y equals plus or minus 2. All right, so this is telling us on this function, any place that the x coordinate is 1 or -1, the partial with respect to x is going to be 0. And of course, anywhere that y is equal to 2 or -2, the partial with respect to y is going to be 0. We need to find the points where they both agree they're both equal to 0. All we have to do is mix and match these y coordinates and x coordinates that we found. So our critical points are going to be any place where x is equal to 1 and y is equal to 2, or x equal to 1 and y is -2. And then we'll do both the same ones for our -1 for x. -1, comma 2. -1, comma -2. All right, so at any of those 4 points, both the x partial and the y partial are both equal to 0. These are going to be our 4 critical points, our 4 potential local maximums and local minimums. All right, let's try one that's a little bit tougher to find the critical points of. So let's take the partial with respect to x and partial with respect to y, and then we'll set them equal to 0. All right, so with respect to x, I'm going to get 4x cubed. With respect to x, the y to the 4th term disappears. That mixed term minus 4xy, we're going to pull off the coefficients, which are going to be minus 4y. And then derivative of 1 is 0. And then same thing for my partial with respect to y. Let's go through and calculate that. Derivative of x to the 4th will be 0. I'll get 4y cubed. And then derivative of minus 4xy, we'll just pull off the constants. And then derivative of 1 is 0. All right, and we're going to set both of these equal to 0. And we're going to try to figure out what points make both of these equations equal to 0 at the same time. All right, the first thing I'm going to do is divide everything in the world by 4 because I've got lots of constants just to make this look simpler. Divide by 4 on both sides. So I get x cubed minus y equals 0, and y cubed minus x equals 0. All right. So I need to figure out where both of these are equal to 0 at the same time. So we can do a little bit of substitution here, which is kind of a variation on a technique that you probably learned in high school. All right, so over on the left here, I'm going to add y to both sides, and I get that x cubed is equal to y. So I can take that expression and plug it in for the y that's in the other equation. So we're kind of solving by substitution here. So over here in the y partial, where I have y cubed, I'm going to make that x cubed. Okay, so that way I've kind of made both equations smush into one equation. All right, so multiplying exponents, 3 times 3 gives me x to the 9th minus x equals 0. I can factor an x out of that, and I get x times x to the 8th minus 1. All right, so let's set both of those factors equal to 0. I set x equal to 0, that's one of my solutions, and x to the 8th minus 1 equals 0. This is a whole lot like solving x squared minus 1 equals 0. I'm going to add 1 to both sides. And instead of taking square roots, I'm going to take the 8th root of both sides of the equation. So squeeze a little 8 in the crook there. And eighth roots are the same as square roots. They're even, so you need a plus or minus when you do this. X is equal to plus or minus 1. All right. So whatever these critical points are, X is either equal to 0 or plus or minus 1. All right, so we just need to find out what the Y coordinates are now. I'm going to go back to that red circled relationship I have there where X cubed is equal to Y, and we'll just figure out what the Y coordinates are. All right, so when X is equal to 0, Y is equal to X cubed. That's just also 0. Same thing, I found X equals plus or minus 1. Y is equal to whatever the X coordinate is cubed. And this is not very exciting. I'm plugging in -1 cubed and I get -1. Okay, so just kind of a coincidence that the X and Y coordinates end up matching. All right, but our three critical points that we get are 0, 0, 1, 1, and -1, -1. So I'm just taking this information over here and listing it in ordered pair form. All right, so those are our potential X, Y coordinate pairs that are going to cause a local maximum, local minimum, or saddle point on this graph in R3. And we're going to need a technique, our second derivatives test that we're going to learn in class, to figure out which ones they might be.